Welcome back to Statistical Minecraft. Today, we're talking about what probabilities are possible in Minecraft, and we'll apply that knowledge to create a sword and axe loot randomizer for a minigame. Let's get into it. Last episode, we inspected random behavior over a long time, creating these graphs. We analyzed droppers and redstone randomizers. The dropper follows a uniform distribution, which means that every one of its item slots can be picked with equal probability. This means that we can put the same item in multiple slots in a dropper and expect to see more of it. In fact, this is what we saw. When we put 1 yellow stack, 2 green stacks, and 3 blue stacks in the dropper, we saw that roughly half of the output items were blue. 50 stacks of each stack, and because 3 of the 6 were blue, we got more blue. 3 of 6 turning into 1/2 is interesting, and it kind of makes sense. What other probabilities can we make in Minecraft? Are there some that are not possible? That's the topic of today. Statistical Minecraft. Improbable! How many different probabilities can we drop items with? Using a single dropper, we're modeling the inside of that dropper with these 9 chiseled blocks, and we can have anywhere from 0 to 9 blocks on the inside. It turns out, if we put all the same item in, it's always a probability of 100 that we get a blue item, unless the dropper's empty. That's a little less interesting. So what happens if we put in a different colored item? If we fill a single slot with a yellow item, we're going to get a half and half probability. And as we keep increasing the number of one of the items, we can get all the way up to 1 in 9 or 8 in 9 for blue. There's this yellow block down here, because these are complementary probabilities. We can just change the 2 colors and get the other one. So we could have 8/9 yellow and 1/9 blue, or vice versa. But what if we wanted a 1 in 10 chance of something happening? Is there a way we could do that? Well, it doesn't seem to be clear how to get that with a single dropper, because there's only 9 item slots inside. Let's come back to that question. For now, let's focus on whether we can use our dropper circuit from last time to simulate any of these states. Could we get something all the way from 1/2 to 1/9? Turns out the answer is yes. That's because of how this dropper works. Our binary, meaning 2 outcome randomizer from last time, receives a pulse on the input line and outputs a pulse on either the yellow or the blue output line. The probability it does so with is determined by this dropper behind me. This circuit is basically a detector for big or small items. Minecraft has big and small items. Light blue wool is a small item. You can stack it to 64. Rafts and boats are a big item. You can only stack them to a stack size of 1. So by changing the composition of large and small items inside this dropper, we change the likelihood of the output. In particular, this dropper looks like this. It's got 8 in 9 chance of picking one of these slots, and a 1 in 9 chance of picking the blue one, which is a lightweight item. When we trigger this, if we lock the top hopper, we'll save what gets spit out. We're expecting it's probably yellow. Yep, that seems to be true. So we've got a yellow boat up here. If we instead had a blue item up here instead of the boat, then we would observe the blue light go on. This is the redstone responsible. Basically, this hopper is either barely full with one of these items, or mostly full with one of these items. That's what this circuit detects. There's a small nuance. When we want to represent, instead of mostly yellow, if we want to represent mostly blue. This comes from the fact that inserting this item into this dropper will stack it with this one, because they are truly the same item. Just by the way Minecraft works. So we want to be careful that we use different small items with this circuit if we want to have multiple chances of small to big. But that's just Minecraft specific, and because the probabilities are complementary, we can just swap the colors and get the same outcome. But don't just take my word for it. Here are the simulated probabilities from 1/2 all the way to 1/9. We're going to run this experiment over a long time and see which colors get picked more often. On this side of me, we've got the 1/2, so we're expecting a roughly equal amount of blue and yellow. And on this side, we've got 8/9 yellow and 1/9 blue, so we're expecting mostly yellow items here. Each of these droppers will be triggered the same number of times, so the same number of concrete powder will fall in each. We're just interested in which color falls more often. Let's take a look and see what happens. Unfortunately, it looks like one of my circuits never activated, the 1/8 one, but we can still see the general pattern. Over a long time, the randomness evens out and we get the expected trend. From roughly equal to blue less and less likely and yellow more and more likely. As a result of the way the relative probabilities work, every successive difference between yellow and blue has less and less of an effect. The curves are really sharp at the start, but smoothen out as they go along. So we can indeed replicate the probabilities from 1/2 to 1/9 with a single dropper randomizer. That's wonderful. But let's get back to that question about 1/10. Is there something clever we could do? We want to get one output of 1/10 probability and another output with 9/10 probability. But we can't do this with our own single dropper circuit, because a dropper only has 9 item slots. However, what we can do is combine droppers to try and achieve this. This is a joined circuit. The top dropper has 4 blue and 1 yellow. This means that it has a 4/5 chance of outputting blue. If it outputs blue at the top, then that continues down this left branch and it's guaranteed to be blue. So 4/5 of the time, or 8/10 of the time, our output will be blue. 1/5 of the time, or 2/10 of the time, our output at the top is yellow. And if that happens, we continue to this dropper down here. Here we have a 50-50 chance of blue and yellow. So remember that 2/10 of yellow coming down from the top. Now, half the time that's yellow, half the time it's blue. In total, 1/10 of the time our output is yellow, and 1/10 of the time our blue output, which it merges with the blue from the other side. So it seems like we've achieved what we wanted. We can get a 1/10 chance of yellow and a 9/10 chance of blue. Note that this works because droppers are independent. The dropper before has no bearing on the likelihood of outcomes in a dropper afterwards. The outcomes of a dropper only depend on its internal state, how its 9 item slots look. This allows us to create a combined circuit like this to get 9/10 and 1/10. Let's see how that compares using our machine over here. Here's a Redstone implementation of the previous circuit diagram. The input pulses in green come from the top. If the branch is blue, then it is output to the blue column directly. And if the branch is yellow, it goes to a second randomizer, where it's 50-50 blue or yellow. We expect this to be 9/10 blue, 1/10 yellow, so let's see what happens. And there we have it, our digital implementation of the circuit diagram for 1/10 and 9/10 probability just completed. The results on the left and right are not completely comparable because we triggered these a different amount of times, but it looks like they're roughly what we expected. The 1/10 is slightly lower than the 1/9, blue on the left, yellow on the right. There's some variation. If we did this for a longer time, the differences would become more apparent. These results seem consistent. We have found a way to chain droppers into circuits that result in composite probabilities. A composite number has factors other than 1 and itself. 10 is composite because it can be factorized as 2 times 5. And indeed, we did compose dispensers to achieve this. We have a 1 in 5 chance and a 1 in 2 chance, which leads to a 1 in 10 chance on yellow. But what about 1/11th? Is there a way to get a 1/11th probability of an output line? Well, we could create 1/10 with consecutive droppers, due to those droppers having independent probabilities, multiplying 5 by 2 to get 1/10. But 11 is a prime number, which means its only factors are 1 and 11. Because of this, we cannot get a 2-output line with a 1/11th chance for consecutive droppers. Unfortunately, we cannot model probabilities for any prime number bigger than 7, because they just won't fit into a dropper. The dropper only has 9 slots. So we can't get them with a single dropper. And because their prime number is not composite, we can't combine droppers in the way we got 1/10 to get 1/11th or any other larger prime numbers. We can't get 1/11th and 10/11th probabilities on 2 output lines. What happens if we start thinking about more than 2 output lines? For example, 1/3, 1/3, and 1/3. Could we achieve this? Well, when we pick from 3 outputs, we need to make 2 choices. We either keep or reject the first item, and we keep or reject the second item. From these 2 choices, we can deduce the outcome of 3 items. If we keep the first item with 1/3 chance, yellow, and we keep each of the 2/3 chances, cyan, with 1/2 probability each, we get 1/3, 1/3, and 1/3. Just like last time, we can compose probabilities to get something more interesting. If the top choice is 2/3 cyan, then it's either 1/2 blue, which composes to be 2/6. It's 1/2 dark blue, which multiplies by 2/3 to be 2/6. Or it was 1/3 at the start, and it stays 1/3 multiplied by 1, which is also 2/6. In this way, we get 1/3, 1/3, 1/3 out of the circuit. And we did that by cleverly varying the probabilities at different steps. Let's run the test. 3 colors, we're expecting the same number of each. We've got the digital circuit. Who knows what'll happen? Well, we kind of do because we're mathematicians. But let's see it anyway. When close up, it looks like there's a difference between the columns, but if we zoom out over a long time, it's not really that significant. This is excellent, especially for game designers, and that's because we can make something that we know is fair. It's 1/3, 1/3, 1/3 chance of getting, I don't know, a sword, a stick, and an axe. But individually, game to game, it's hard to say what the outcome will be. It's random. This makes for really fun gameplay. So we can get multiple branches. That's quite exciting. Maybe we can use this multiple branches trick to get that elusive 1/11th. You might be thinking, Thunderquirk, we can just get 1/11th like this, because we take one to the side, put the rest on the left. One to the side, rest on the left. In this case, we had 1/3 to the side, 2/3 to the left, and then at the base case, 1/3 and 1/3. But again, because 11 is prime, we can't do this. This is because we're composing again, right? We rely on this multiplication of 2/3 and 1/2 to get 2/6. But 1/11th doesn't have factors. So unfortunately, we can't use this trick. There is a sacrifice we can make to get 1/11th. There's something implied that we haven't stated so far, which all of these circuits share. And that is the condition that they terminate. Up to this point, all of the circuits we've constructed take an input once, and that input flows only forward. It never goes back again. This property is called being monotonic. It's a property of monotonicity. The circuit impulse always goes to one dropper, and then to another dropper, and so on until reaching the pistons. This means that every time we push the button, we know that the pulse moves only forward, and the piston will be pushed once. We can estimate the time that will take. That's a useful property, because we have information about when we should expect our calculation to finish. We know that there's no recursion happening, so at worst, the impulse will take the number of randomizers to traverse from back to front. In this case, the best case is this yellow branch. It gets activated really quickly, and you just saw that in the time lapse. In the worst case, we have to go through this randomizer to the cyan branch, and then another randomizer. But we know that there's a worst case. We know it's finite, and it's 2 at worst. If we sacrifice this condition, we can get prime numbers. This is a circuit to achieve 16 outcomes with equal probability. As we can see, it's a bunch of binary decisions of 50-50. At the top level, we have a half chance of going left, a half chance of going right, and this pattern continues until we get all the way down to 16 different output lines, in gray at the bottom. We can modify this circuit to get 1/11th at every outcome with equal likelihood by adding a recursive branch. Let me show you. We can close off and restrict some of these outputs to be orange, and the orange line takes 5 of them and goes all the way back to the beginning, back to the start of the system. What this means is that instead of observing 16 outcomes with equal likelihood, we now only see 11 outcomes with equal likelihood, because these 5 will never be shown to the outside of the circuit. If any of these 5 are reached, they'll go back to the start and try again, and they'll keep trying again until one of these 11 is reached. At that point, the pulse continues outside the circuit. This sacrifices the termination guarantee, because in the worst case, this cycle never ends. We can keep rolling one of these 5 branches over and over and over and over again. And the only way to know that we've reached the end is to add a detector on these 11 that tells the system, oh, this circuit has finished computing. Whereas this orange line capped the outputs and put them together so that all 5 of these would re-roll, this green line also takes information from each of these outputs. Unlike the orange, these outputs can continue going to whatever systems they're meant to trigger. But if any of these triggers, this green line is activated, which tells the circuit at the front, okay, we can now receive another pulse to reroll. This green line helps us avoid the situation where we send a pulse, it trickles down, and then we send another pulse. But the first pulse might have gone to the beginning, And so now we have 2 pulses coming in and acting unpredictably. We want to make really, really sure that we're only processing 1 pulse at a time. And this green line can help us ensure that by acting as a gate. Basically, we're telling the system, you've sent a pulse, now wait, and until you hear from the green line that we're done, don't send another pulse. This is the only way we can make sure we know for certain when a pulse is done being processed by our 1/11th circuit. We need this detection line to run. Otherwise, this could be looping forever and we'd never know when to send another pulse. There is an optimization we can make. A lot of these branches on the leftmost side are not actually useful because we know that no matter what the output of the first 4 here is, it's going to be orange. We're going to reroll. So we can take out these branches, these trees of randomizers, because they don't actually give us additional useful information. This saves a little bit of resources, and it saves some time calculating when we know that we'll reroll as soon as this orange behind me triggers. The amount of redundancy we can reduce depends on the number we want to calculate. If you need to construct an arbitrary prime number with equal probability on the outputs, pick the power of 2 that comes next. For example, we had to get 1/11th, so we picked 16, which is 2 to the 4th. Then we eliminated all the outputs we needed, and then we simplified. We noticed, oh, we had 16, we needed 11, so we subtracted 5. 5 is 1 plus 4. And so because of that 4, we can combine these. We know that these 4 outputs came from the same branch. So we can simplify a little. The last trick you might need to make any number distribution you want is to combine the outputs of these 11s. I tried to come up with a pathological output combination. We have 1/11th, 2/11ths, 3/11ths, 1/11th, and 4/11ths. So this is a circuit for 5 outcomes with these probabilities. There is one more optimization we could make here, but the general idea is that you build your circuit, you pick a power of 2, like 8, 16, 32, 64. You then make some of these branches recursive so that they re-roll and don't count. And finally, you group the branches as you need. This allows you to make a Minecraft randomizer with any probability on the output branches. You can have fine-tuned control of what you need. But we are sacrificing something. We're sacrificing that guarantee of termination. This circuit is a lot more complicated than the ones we had before, because we have this orange line to reroll, and we have this green line to let the system know when it's safe to send another pulse. So up to you. If a simpler probability works well enough, consider that one. But if you want to be really precise, you can, which is awesome. This is one way to optimize the final circuit. We've tracked the combined branches up to see where they come from. So we can replace a lot of this tree on the right, a lot of this brown tree, and some of this light gray tree in the middle. This makes it so we get outputs from the circuit faster and can keep using it more quickly. This is the last optimization that we'll discuss today. So if you need to make an arbitrary circuit, you now know how. Let's check it out. That took a long time, translating this into this. Notice, there are not many randomizers, these white blocks, but the wiring is pretty intricate. We even had to go 3-dimensional. I didn't leave enough room for this brown line from back here to connect to this brown line over here. And we definitely had to go 2-dimensional for this green line, the approver. What we're going to do is set this up in an infinite loop so that a pulse either comes back to the start from orange or from green, and I'll just manually shut it off instead of having this circuit as usual. We could set something up to have memory, but this seems simpler for a demonstration. Basically, this is complicated. If possible, try to have a simpler circuit than a prime number circuit with recursion. Recursion makes things hard. Okay, I'll finish this, and let's see how it performs. We've got the powder in place and the circuit fixed up. Let's see what happens. Which column do you think will reach the top first. Green was the most common, and that makes sense because green is the count of outputs. So gray plus light gray plus brown, all of it. Green is that height. Orange is the next highest. It's higher than any of these outputs. And that's because orange triggers 5/16 of the time. Orange will never trigger more than half of the time. Because if this was the case, we could just remove that branch of the binary tree completely. In expectation, orange will never be more than half of the outputs we see. And that's because if the first 8 of these 16 branches were orange, then we could have just removed the full orange branch entirely. If 9 of the 16 were orange, then we could remove the left branch entirely and only use the last output, the 9th one. So this gives us a little bit of a bound in expectation on the recursion. But what, you may be asking, is any of this good for? Why do we need this complication? Well, having reliable, precise statistics in Minecraft is helpful for minigame designers. Let's consider designing a minigame right now. Let's say that I'm designing a dungeon crawling, deck building, collect them all, trading game. My game has loot drop points with the following dropper distributions: 3 iron swords, 2 gold axes, 2 potions of poison, a lingering potion of poison, and a fishing rod. However, what astute viewers might notice is that none of these items are stackable. So how do we refill the dispenser when it throws an item out? We can use our statistical Minecraft knowledge, of course. Instead of having one dispenser that stores one of each item, and then when it vanishes it's unclear what to replace it with, we can instead use our randomizer circuits hooked up to different dispensers, one for each of these items, with different probabilities. Let's do that. With a dropper of this internal state, we have a circuit diagram of this internal state. 3 swords, 2 gold axes, 2 potions, 1 lingering potion, 1 fishing rod. And this is one way to create a circuit that fulfills that. Here, I've labeled each dropper by the relative position of the items in the original dropper. Fishing rod and lingering potion are light blue in the first decision, or it's 7/9 of something else. That something else breaks down into 3/9 of sword and 4/9 of something else, and that last 4/9 breaks down into poison or gold axe. Now, because we have our redstone signal coming out for each of the weapons, we can make a circuit to do this, and have 5 droppers drop down a hole, so they drop items, with the right probabilities. Pretty sweet. Let's build that circuit. Now that we have our circuit diagram, it's pretty easy to translate that into the redstone circuit we need. This looks very similar. We've got 5 branches coming out, and we've got our dropper randomizers where they ought to be, and these probabilities here tell us what probabilities to put inside them. Each of these droppers faces into a column that'll drop out onto the drop point, and we can make this column arbitrarily tall. That means we can put as many items in this drop point as we need. It doesn't have to be just 9. We can put more than 9 types of items here, controlled by the circuit. We can do non-stackable items because we can put hoppers with tons of chests feeding into these droppers, so that potions, armor, swords, boats will never run out. We only rarely have to restock, because we can have massive bulk storage behind them. This is awesome for replayability, especially if your game is played thousands of times. Let's finish up the circuit and see how it works. And just like that, our randomizer is complete. Our item drop station is populated with tons of items. We've got a clock hooked up so we can observe what happens in the long run. Let's go for it. Let's see what the distribution is. Mostly swords and poison, and axes, and a few fishing rods, and a few lingering potions. That's pretty good. And the system won't have to be refilled for a long, long time. We've still got plenty of items in here. So there you go. You can now create drop points for your minigames with non-stackable items that are not limited in either size or number of items, like we mentioned. This only has 9, but we could do many, many more. We could do 16, we could do 11, we could do any number we wanted. With the power of statistical Minecraft. Thank you for watching. You can now make any probability distribution you like in Minecraft, assuming you know the probabilities of the outcomes you want. Let me know what you found interesting, and what you might be curious about in the comments. Have a good one!